Hello again. This is section 2.4, average rate of change of a function. And so what we're going to look at in this section is how do we calculate average rate of change, both from a function that's given and then also from a graph of a function. And then what does the average rate of change actually mean about that function? Okay, so our average rate of change of a function between some value x equals a and some value x equals b is going to be the change in y over the change in x, or f of b minus f of a divided by b minus a. Now, that might sound familiar because all this really is finding the slope between 2 points, right? So a change in y divided by a change in x is like a rise over a run. So we're really just calculating a slope. Now, specifically, we're calculating the slope of what we call a secant line between 2 points, A and B. So if you look at the graph below, we have a point A, we have a point B, and we're just saying that if I have a point on my curve at A and I have another point on my curve at B, and I draw a line through those 2 points now, the average rate of change along that curve is just going to be the slope of the line between those 2 points. Okay, so that's all we're calculating when we find average rate of change. All right, so now we have a function here, x minus 3 squared, whose graph is shown in the figure in the book. Okay, so if you want to take a look. But in this case, we're just trying to find the net change and the average rate of change between the points that are given. Okay, so the first 2 points here are x equals 1 and x equals 3. So the first thing we need to do is identify what's our a and what's our b. So the 1 is going to be the a value, and 3 is going to be the b value. So to find net change, right, because that's the first thing we're asked to find here, remember that formula is going to be f of b minus f of a. So that's the first thing we're trying to find. So now all we have to do is just say, well, the b value is 3, so that's going to be f of 3. The a value is 1, so that's f of 1. And now we're going to substitute those into our function to find those actual values. So f of 3 is going to be 3 minus 3 squared minus, and then f of 1 would be 1 minus 3 squared. And then if we simplify all that now, 3 minus 3 is 0, 0 squared is 0. And then 1 minus 3 is going to be a negative 2, but negative 2 squared becomes 4. So we have 0 minus 4, which gives us negative 4. Okay, so that is our net change of our function between the values of 1 and 3. Now, the next thing we want to find is the average rate of change. And so that's our new formula. So average rate of change. And so remember, that's going to be f of b minus f of a divided by b minus a now. Well, f of b minus f of a is just the net change. That's what we just calculated. So I know the numerator piece is just going to be negative 4 now. And then the b minus a piece is just going to be the 3 minus the 1. Okay, so now we just have to simplify that. So we're going to have negative 4 over 2. And if I divide negative 4 by 2, that's going to give us negative 2. And so my average rate of change along that function between the values of 1 and 3 is going to be negative 2. Or in other words, the slope of the secant line between 1 and 3 on my graph should be a negative 2. All right, so now in B, we have two values again. The 4 is going to be your A. The 7 is going to be the B. So again, if we're looking at net change first, we're going to calculate f of b minus f of a. That's going to be f of 7 minus f of 4. Again, we're going to substitute those values into our function. We're going to have 7 minus 3 squared minus 4 minus 3 squared. And then simplifying that, 7 minus 3 is 4. 4 squared is 16. 4 minus 3 is 1. 1 squared is 1. And then 16 minus 1 is going to give us 15. And so our net change is going to be 15 for that one. And then if we're looking at average rate of change, again, just to remind us of the formula, it's going to be f of b minus f of a divided by b minus a. Again, we already calculated the net change, which is the f of b minus f of a. That gave us 15. And now b minus a is just going to be 7 minus 4. Simplifying that now gives us 15 over 3. And 15 divided by 3 is just 5. And so our average rate of change, or the slope of the secant line between 4 and 7, is going to give us 5 now. Now, we're not always going to need to calculate net change first, but in this case, it's actually pretty useful because it gives us the numerator for the average rate of change anyway. Okay, but if they don't ask you for net change up front, you're still going to have to calculate that numerator the same way we did for net change, and then you're just going to have to divide it by the difference between the b and the a values. All right, so now example 2, we have an object dropped from a high cliff or a tall building. The distance it has fallen after t seconds is given by the function d of t equals 16t squared. So we want to find the average speed, which would be the same thing as the average rate of change, right? Because speed would just be a distance over a time, which would be like a slope or an average rate of change for each of these intervals. Okay, so the first time interval they give us is 1 second to 5 seconds. We're just trying to find the average rate of change or the average speed over that. So the a value is 1 this time, and the b value is 5. So if we're looking for average rate of change, this time it's going to be d of 5 minus d of 1 divided by the b value minus the a value, so 5 minus 1. Okay, now we just have to substitute those values in. So we're going to have 16 times 5 squared minus 16 times 1 squared all over, and I'm going to go ahead and subtract 5 minus 1. That's going to give us 4. Now it's just a matter of simplifying the numerator here. So we're going to have 16 times 5 squared. Well, 5 squared is 25, and if I multiply that by 16, that should give us 400. 1 squared is 1 times 16 is 16. And if we subtract that now, 400 minus 16 should give us 384. And if we divide that by the 4 in the denominator now, that should give us 96. And so 96 is our average rate of change. Now we have to keep in mind in this case, right, that we do have a context. So we probably want to think about what these units are going to be. Now on this particular problem, they don't really tell us what distance is measured in. This should be in meters though. So we're going to say that this distance is measured in meters. And so this speed would be in meters per second. So whenever you're dealing with speed, it's going to be a distance over a time. They tell us here that our time is measured in seconds. We had 1 second and 5 seconds. And then our distance this time should be in meters. So 96 meters per second would be our speed. All right, now in part B, we're going to use that same formula. This time, the a value is actually just going to be a, and the b value that's given is a plus h. So when I do this, this is going to be d of a plus h minus d of a all over b minus a, which is a plus h minus a. So this time we've only got variables to substitute in, okay, but that's exactly what we're going to do is plug those into our function. That's going to give us 16 times a plus h squared minus 16 times a squared. All over, and then notice here, when we have a plus h minus a, the A's are going to cancel, and so all that's left in the denominator now is an H. All right, now we have to simplify what we have in the numerator. Well, I can go ahead and square the A plus H. And so A plus H squared is going to give us A squared plus 2AH plus H squared. And that's just using one of those formulas from back in chapter 1, right? If we have a perfect square, right, when we square that, it should give us that. And then minus 16A squared all over H. All right, and I'm going to continue down here. So the next thing I'm going to do is distribute the 16. So that's going to give us 16A squared plus 16 times 2AH would be 32AH. And then 16 times H squared would be 16H squared minus 16A squared all over H. All right, now if we combine like terms in our numerator, 16A squared minus 16A squared, those terms are going to cancel out. And so now we're left with 32AH plus 16H squared all over H. Well, I have a common factor of H in my numerator now, so I can factor that out. So I'm going to factor out just the H here, which leaves us with 32A plus 16H all over H. And you might be asking, well, why didn't you factor out the 16? Because that's a common factor too. We could, right? So if you wanted to factor out the 16, you could. The main thing here is I'm trying to cancel out that H in the denominator. So I really just want to make sure I at least factor out the H here. So now I can factor out and cancel out the H, which is just going to leave us with 32A plus 16H. And so that right there would now be the average rate of change of our function on an interval from A to A plus H. Now, the reason this is useful, right, because you might be saying, well, who cares, right? I don't even have a time limit in this case. These are just random variables. The reason we care about something like this is if we can get a formula like that, now we could choose any value for a starting time and any value for an ending time that we want, and we have a formula that's always going to calculate the average rate of change without having to do it over and over and over again. Okay, so if I just choose a random A value of, say, 5, and then I want a random B value of 7, I know that the 7 is just 5 plus 2, so I have an H value, I have an A value, and I can plug those in and find the average rate of change between 5 and 7. So by generating a formula like this, it helps us with just being able to calculate any time intervals we want without having to do the process over and over. All right, example 3. So the table here gives the outdoor temperatures observed by a science student on a spring day. We want to, it says draw a graph. We're actually just going to use the table this time to help us find the average rate of change of the temperatures between each of the following times. All right, so if I want to look from 8 a.m. to 9 a.m., here's how we're going to think about this. This first column here is going to represent our X values, and then this column over here is going to represent our F of X values. So when I do this now from 8 a.m. to 9 a.m., the 8 a.m. is like the A value. The 9 a.m. is like your B value. So then over here, that's where we're going to get the F of A and F of B that we need for our average rate of change formula. So when I do my formula now, remember it starts with F of B minus F of A. So that's going to be 40 minus 38 over, and then we're going to do B minus A, which is just going to be 9 minus 8. Now we simplify. 40 minus 38 gives us 2. 9 minus 8 is 1. And 2 divided by 1 is just going to give us 2. Now, again, because we have a context, let's think about what these units represent. The numerator here was a difference in temperatures, right? So that's going to be a degrees. And then the difference in the denominators here, those were times. Those are measured in hours. So our units this time are going to be in degrees Fahrenheit per hour. In other words, from 8 a.m. to 9 a.m., our temperature went up by approximately 2 degrees Fahrenheit per hour. That's our average rate of change. And we're going to do the same thing with these other ones. So again, we have to identify the A and B values first. So here, 1 p.m. is going to be our A value. 3 p.m. is going to be our B value, which means that this value over here is F of A, and this value here is going to represent F of B. Again, using our average rate of change formula, we start with F of B. That's going to be 67 minus the F of A, which is 62, over, and then B minus A is going to be 3 minus 1. Now, if we simplify that, 67 minus 62 should give us 5. 3 minus 1 is 2. And if you wanted to get a decimal for that, you could, or you could just leave it as the fraction. Either way is fine. This would be 2.5 as a decimal. And again, our units are still going to be the same as the previous one. This is degrees Fahrenheit per hour. Or we could say that our temperature is rising by approximately 2.5 degrees per hour. And then the last one here, we're looking at the hours from 4 to 7. So 4 is going to be our A value. 7 would be the B value. Now we have our F of A over here, F of B down here. Again, we're going to start with F of B. So in this case, that's 51 minus F of A is 64 over B minus A, 7 minus 4. Now we subtract. 51 minus 64 is actually going to give us a negative 13. Then we're going to divide that by 7 minus 4, which is going to give us 3. Now, again, if you want to get a decimal, this one's going to actually be a repeating decimal, but we can round it off. This is approximately negative 4.3 repeating. And then again, this is going to be degrees Fahrenheit per hour. So again, what this tells us now is that between the hours of 4 p.m. and 7 p.m., our temperature is decreasing by an average rate of 4.3 degrees Fahrenheit per hour. Whenever you get a negative average rate of change, that just tells you we have an average rate that's decreasing. And in this case, it's decreasing by that number of degrees per hour. All right, example 4. So now we're going to let our function be 3x minus 5. We want to find the average rate of change between each of the values that's given here. So same formula we've been using. Our A value this time is going to be 0. B is going to be 1. So we're going to find F of 1 minus F of 0 divided by 1 minus 0. So now we just substitute our values into our function. That's going to give us 3 times 1 minus 5 minus, and then I'm going to do 3 times 0 minus 5. All over 1 minus 0, which is just 1. Now if we simplify what we have up top, 3 times 1 is 3, minus 5 is a negative 2, minus 3 times 0 is 0, minus 5 is a negative 5, all over 1. And then we have negative 2 minus a negative 5. Remember, when you subtract a negative, it becomes addition. So this actually becomes 3 over 1, which is just 3. So our average rate of change between 0 and 1 this time is going to be 3. All right, now same formula. This time our A value is going to be 3. B value is going to be 7. So we're taking F of 7 minus F of 3 all over 7 minus 3. Substitute that into your function. So we'll have 3 times 7 minus 5 minus 3 times 3 minus 5 all over 7 minus 3, and I'll go ahead and simplify that. That's going to give us 4. All right, now simplifying the numerator, 3 times 7 is 21, and then 21 minus 5 should give us 16. And then in here, 3 times 3 is 9, minus 5, that should give us 4. And now when we subtract 16 minus 4, that's going to give us 12 over 4. And 12 divided by 4 is going to give us 3. All right, and then the last one here, the A value is just going to be A. The B value is going to be the A plus H. We're going to take F of A plus H minus F of A all over A plus H minus A. All right, so again, just substituting into our function, we're going to have 3 times A plus H minus 5 minus 3 times A minus 5 all over, and in this case, the A plus H minus A, those A's are going to cancel, and so my denominator is just going to be an H this time. All right, now if we distribute here, that's going to give us 3A plus 3H minus 5. And we can distribute the negative to everything in the brackets there. So it's going to be minus 3A and positive 5 all over H. And then I'll continue down here. The 3A minus 3A, those terms are going to cancel. The negative 5 and the positive 5, those terms are going to cancel. And so we're really just left with 3H over H. And if I divide 3H by H, the H's will cancel, and we're just left with 3. Now, the thing that we need to recognize on this problem, in part A, we got 3. In part B, we got 3. And in part C, we got 3. The reason for that is that our original function was actually just a linear function. Its slope is 3. Therefore, the average rate of change between any 2 points on that graph is always going to be 3. It's always going to be the slope of whatever the line is. Okay, so without having to really do too much work at all on any of these problems, if you just recognize, okay, I've got a linear function, I know the slope of that line, therefore the average rate of change along that line is always going to be 3, no matter what 2 points I choose. Okay? So just try to keep that in mind when you're trying to solve these problems. If you see a line, just know that the average rate of change is the slope of that line. All right, and so that's all we've got for this section. Again, always send me questions as you have them in WebAssign. Let me know if you need to meet with me for any reason. Come to my student hours if you need to. But otherwise, I will see you next time.